Hello once again, class, and welcome to another mock lecture. Today we're going to be going over in just one example, really, of using logarithms to solve an annuity problem. So let's just jump right into the example. All right, example number one. The only example. Kronk wants to have an annuity savings of $1,700,000 in his account by the time that he retires. If he deposits $1,250 into the account every month at a 6.2% APR, how long will it take to reach his goal? Okay, so the first thing that we need to look at is this question is asking us how long. Anytime you're solving for a length of time in an annuity or in a payout annuity or in a compound interest problem, you're always using a logarithm to do that because the exponent is where the variable lives that we're trying to solve for, right? That's where the time variable lives. Okay, so here, So here's the annuity formula for which I just plugged in all the information that we needed to know. So like this was our P sub n. That's how much we want to have. That's how much Kronk wants to have by the time he retires. Here's our APR, right? So that's R, right? But it's as a decimal, so I did it as 0.062. This is your initial deposit. Or I guess in an annuity sense, it's not an initial deposit, it's the monthly deposit. And then, is that everything? Oh, and then we know that it's happening at a monthly interval, and so that's why we have 12 as our K value, because it's a monthly deposit. Okay, so what we're going to do is we need to isolate this thing. We need to always, anytime you're using a logarithm, or I guess I really should say, anytime that you're solving for an exponent, you want to isolate the base of that exponent. The base in this case, I didn't mean to rhyme there, but the base in this case is 1 plus 0.062 over 12. So we need to get that thing by itself. And of course, it's raised to the 12n, which is why I included it in the thing that we want to isolate. There's three things we need to do that. We need to move all these things over to the other side of the equation. So I'm going to start by multiplying both sides, and we're going to do the work on this one thing, and I'm just going to kind of manipulate this one expression, or rather equation, until we have our answer. But the first thing I'm going to do is get rid of the denominator. This whole thing here is being divided by this. So I'm going to multiply both sides by 0.062 over 12. Okay, and that looks like this. So it cancels on this side and we're left with this. The next thing I'm going to do is, this whole thing is in parentheses. It's being multiplied by 1,250. So we need to divide both sides by that so that they'll cancel on the right-hand side. All right, so now we're left with this. We don't need the parentheses anymore because nothing's happening. And then I need to get rid of the 1. So I'm going to add 1 to both sides, which means that it'll cancel on the right. And then here we go. We finally have the base isolated, which is why now we're going to take a log of both sides. Anytime you're solving for an exponent and you just have the base and it's raised to that exponent, you can use the logarithmic property that says, hey, if you run both sides through a logarithm, you can bring down the exponent in front of the logarithm. So that's what we're going to do. Whatever you do to one side, you always got to do to the other. So we're taking a log of both sides of the equation, really just so that we can bring this 12n down in front of the logarithm. Now it's important to know the whole exponent comes down. So 12n is the exponent that comes in front of the logarithm. And now we want to try to get this by itself. It's being multiplied by these two things. So let's just divide both sides by those two things. 12 times the log of 1 plus 0.062 over 12. The 12s will cancel. The log 1 plus 0.062 over 12s will cancel. And you're just going to get n by itself. And then I just went and I plugged this whole thing exactly as it is into Desmos. Right? These are the same. And it spit out 33.7 years, as that's me approximating. Okay, so it'll take Kronk 33.7 years to reach his goal. A couple things to mention. Notice that I didn't ever round anything. I didn't actually do the calculations here. Like I didn't calculate this and then divide by 1250 and then calculate this and then add 1 and then calculate that and then take the log. Because I don't want to round too much. There's a lot that could be rounded enough times that would alter the answer. Like it's in the realm of possibility that we round at every single step, and instead of 33.7, which is the answer, we get something like 34, right? Or 35, right? Even that, something like that is possible depending on how aggressive you're being with your rounding. So I don't round anything, and I just plug it into Desmos exactly as it shows up in my work, and that's how I get my answer. Okay, so that's it. Here's all the work in steps if you want to pause here and kind of look through the video, or rather look through the slides. But that's all for this one. Hopefully you guys learned something. If you have any questions, just shoot me an email or leave a comment in the video. Thanks a ton for watching, and I'll see you in the next one.